Alright, this is the solution video to problem D from Codeforces LATOKEN round 1. Now, it's a tree problem and it's interactive. So if you haven't read the problem statement yet, then definitely go check that out first before you look at this video, because this problem is actually pretty interesting in my opinion, and I think it's pretty educational as well. So to start things off, you're given n, which is a number of nodes in a tree, and there also exists like this tree of n nodes. And the thing is that you don't actually know what this tree looks like. And what you're trying to find is you want to find all n-1 edges. So in other words, you want to find what the structure of a tree is. And in order to do that, you can make one type of query where we pick any node in this tree, and then we'll receive the distances from all of these nodes, from all n nodes, to that node that we picked. So for example, if we picked this node over here, let's assume this is just like 1, 2, 3, 4, 5, 6. We pick node 2. We're going to receive the distances of the distance from 1 to 2 is 1, distance from 2 to 2 is 0, distance from 2 to 3 is 1, distance from 2 to 4 is 1, distance from 2 to 5 is 2, and distance from 2 to 6 is 2. So this is what we're going to receive from one query. And we want to make at most ceiling of n over 2 queries to find what all of these edges are in this tree. So there's basically one important observation that you have to make in order to solve this problem. And what that observation is this. Well, okay, before I get into what this observation exactly is, I guess I'll explain what my thought process was. So if we have some node, or I guess not a node, some edge, we know that it connects two adjacent nodes in this tree. We also know that all trees are bipartite, meaning that if we were to do a two-coloring of any tree, there's always a way to color the nodes in a tree in such a way that all adjacent nodes are different colors. So in this case, if we color this one black, this one has to be white, which makes this one black, which makes these two white, which makes this one black. So this is a valid two coloring of this tree. And all trees have a two coloring like this. So we want to use this property of two coloring to our advantage. And the way we do this is think of it like this. Every edge in this tree connects a black node to a white node. So every edge in the tree will look something like this. So what this tells us is that if we focus on only querying black nodes or querying white nodes, then we can actually get all the information we need. And that's because that if an edge from node A to node B exists, this means that the distance from A to B is equal to 1. This is the only time in which an edge from A to B will exist. And that's because if it's like distance of 1, then obviously you just travel one edge and it's an adjacent edge, or like a node adjacent to that edge coming from the initial node. So what can we do with this? Well, we know that if we query either all of black, if we get like the source distances from all the black nodes or from all the white nodes, we can actually find out what all of these edges are by checking which distances are equal to 1. So under what condition is like this is equal to 1? This means there's an edge connecting A and B. And so keep in mind that we have at most n over 2 queries, like ceiling. So if n is even, then it's just n over 2. If n is odd, then it's n plus 1 over 2. Like we just simply get an extra query if n is odd. So let's start by making an arbitrary query on any node we want. Let's say it's node 1. So if it's node 1, then we'll get like some set of like values from this query, right? It doesn't really matter what it is. So like, for example, if it's like this, so on. It doesn't have to be rooted because that's not a requirement, doesn't really matter. Something like that. So this is what node 1 is. So keep in mind that if we color node 1 to be black, and we do a 2 coloring on the entire tree, all black vertices will be an even distance away from 1, and all white vertices will be an odd distance away from 1. So in the first query, we can actually determine the 2 coloring of the tree. So for example, if this 1 was like a black node, so keep in mind if this was a black node and this is node 1, where like we start the first query, we know that this node has to be black, this node is black, this node is black, and this node is black. I think that's it, yeah. And we know that all of these black nodes are an even distance away from 1, and all of these white nodes are an odd distance away from 1. So here's the important thing. By pigeonhole principle, the minimum of the number of black nodes, or I guess, is it pigeonhole? I think it is pigeonhole. Yeah, I guess it is pigeonhole. So the minimum of the number of black nodes and number of white nodes is at most the floor of n over 2. Because think of it like this. If n is even, then obviously we can have the same number of black and white nodes. If n is even and the number of black nodes is not equal to the number of white nodes, then either there's more black than white or there's more white and black. And the minimum of those two is guaranteed to be less than half of it. And the same thing applies if n is odd. And so this formula generalizes everything. So what this implies is that we can actually just figure out which one of these colors has fewer elements or fewer nodes in this group and just query all of those elements. So for example, in this case, because we know that there's 1, 2, 3, 4, 5 black nodes and 1, 2, 3, 4, 5 white nodes, that was not intentional, but either way, this actually like explains a pretty good, I guess, special case, because the number of black nodes is equal to the number of white nodes. However, because we've already made one query to determine what the color of these nodes are, we have to continue querying these black nodes, because if we query these black nodes, we only need to add 4 more queries. So 1 plus 4 is equal to 5, which indeed is less than or equal to the ceiling of n over 2, because in this case, n is equal to 10. But if we were to just figure out this coloring, and then we query all the white nodes, then it's 1 plus 5 is equal to 6, which is greater than the ceiling of n over 2, which in this case would use too many queries. So we do have to be careful in like choosing which color we stick with. And by color, I mean like what parity of the nodes of a group. What parity do we care about that has a distance that's either even or odd with respect to node 1. So yeah, that's basically how problem D works. Pretty much, you first notice that a bipartite coloring, or like if you do a bipartite coloring of a tree, querying all the vertices of one color is sufficient to get the answer, because every edge in the tree connects one black node to one white node. So querying like all the white nodes will give us access to the black nodes, because it'll just tell us all the nodes that are a distance of 1 from all white nodes, and vice versa. So yeah, that is problem D. I hope this was helpful, and if you have any questions, just leave them in the comments and I'll try my best to answer them. Peace.